All right, we're now going to talk about forward differences. So, as you can imagine, if you open up a table full of values of statistical functions, you're going to see values which are equally spaced. So, you would have, let's say, you have the value of some function for 0.123, 0.124, 0.125. And once again, the question is, how do you find those in between values? Well, if the values are in fact equally spaced, in this case the difference is 0.001 in each of the values, then you can do a few simplifications to the difference and interpolation formulae. So we're assuming that there is some constant spacing between the x values. Let's call this h. So h is the distance between x0, x1, x2, and so on, and we have a fairly simple relevance formula for the relationship between h and x. So we can say that x at some index k is actually x at some index k minus 1 plus h, because h is the distance between each of these. Or if we're starting at x0, then xk is simply x0 plus k times h. Fairly obvious stuff. But now we're going to actually define something called a first forward difference. So let's write this down. First forward difference. Okay, so what is this first forward difference? Well, essentially, the first forward difference, which we'll define as delta fk, is simply the function at k plus 1 minus the function at k. It's probably worth illustrating at this point what we're talking about. So essentially, if you imagine a chart like so, you have some function going like this, basically, then if we're taking two values, let's say the x at index k and x at index k plus 1, then if you look at the actual value of the function that this produces the value fk, and this produces the value fk plus 1. So the distance between these 2 points is called delta fk. That's the first forward difference. And then we can define the second forward difference. So the second forward difference is as follows. So that's going to be delta squared fk. So delta squared fk is defined as the difference between the deltas at k and k plus 1. So that's essentially delta f k plus 1 minus delta fk. And we can sort of go on with this and define the higher forward differences. So then we can apply our knowledge of divided differences that we have from before, and we can actually try to define those divided differences in terms of these forward differences that we have right here. So the first divided difference, so f with square brackets with x0 and x1, if you remember the definition of the first forward difference, it's essentially f1 minus f0 divided by x1 minus x0. However, we know that f1 minus f0 happens to be delta f1 by the definition of the first forward difference that we've introduced. So we can define it as delta f0 divided by h. And similarly for the second divided difference, so f with x0, x1, x2, that's going to be defined as a similar formula, but with the first divided differences plug in, and we're already taking these values and plugging them in. So that's going to be delta f1 divided by h minus delta f0 divided by h, all divided by 2h. And what we can do here is we can note the fact that delta f1 minus delta f0 happens to be the second forward difference, delta squared fk. So we can rewrite it. We can take the h and move it down. So this becomes 2h squared. And on the top we have delta squared f0 divided by 2h squared. And if you continue this idea, if you expand it to further divided differences, you'll get the following formula. You'll get the divided difference between x0 and a couple of points until some xn, being defined as delta to the power n f of 0 divided by n factorial times h to the power of n. So that's the formula that we are going to use, and we can formulate a new table. Remember when we were solving with divided differences, we had this table which was kind of like a converging triangle. We can define another one of those. So you can think of, once again, we'll talk about the x values. So you'll have the x values, x0, x1, x2, x3, and so on. And then you would have the function values, so f0, f1, f2, and f3. And then the f0 and f1 would become delta f0, delta f1, delta f2. And then you would have the delta squared f0, delta squared f0, delta squared f1, and then you'd have delta cubed f0, and that would be a corresponding table, similar to the tables that we had for divided difference. And what this is called is a forward difference table. Forward difference table. Okay, so what we're going to do now is a bit of a trick. We're going to do a change of variables so that instead of talking about discrete points like 0 and 1, remember we have to find the values between the points. So we can introduce some variable which will indicate how far we are in terms of h, because the distance between these 2 points is h. The distance between these 2 points is h. But we might want to get, for example, h over 2. So we're introducing a change of variables here. We're basically saying that we're going to define x as being equal to x0 plus some variable p multiplied by h. And p does not have to be a whole number. So essentially, if you want x1, then yes, you multiply h by 1, and you get effectively x1 equals x0 plus 1 multiplied by h. But our goal is to find those in-between values, and for that we would plug in smaller values of p, like for example the value of p equal to 1/2, meaning that if you have points x0 and x1, then setting p equal to 1/2 basically gives you the point that's actually in between these 2 points. That's what the whole procedure is all about. It's finding those values between the lines, so to speak, and then we can formulate the Newton's divided difference formula in terms of this new notation. So let's have a new formula. So we're looking at f at x0 plus p multiplied by h, which is equal to f of 0 plus p multiplied by delta f of 0 plus p times p minus 1 divided by 2 factorial delta squared f of 0 plus p times p minus 1 times p minus 2 divided by 3 factorial delta cubed f0, and so on. So this is our Newton's forward difference formula. Important concept because we're going to use it in a moment. So let's take a look at an example. So here is a not so small example of some function. So let's actually have a few more values than we typically have. So I'm going to have a table of x values and a table of f of x values. Now in this case, I'm going to deliberately use a function which is quadratic so that we're going to have a very nice formula. It doesn't always, you don't always get the formula which matches the numbers exactly, but here we'll have some values of x. Let's have 0, 4, 8, 12, 16, 20, and 24, for example. And then we'll have values of f of x, so it's going to be 3, 59, 275, 651, 1187, 1883, and 2739. Doesn't really matter what they are because we're really only interested in the top diagonal for the forward difference. So essentially, we want to find the first forward difference. First of all, remember we have this table. So the first deltas are actually easy because they're just the differences between the f of x values. So you get something like 56, 216, 376, 536, 696, and 856. Okay, so that's easy, but the second differences are what we're really concerned with. So these are essentially all identical. They all have the same value. In this case, it's going to be the value of 160 in each one of them, which gives us an indication that we're matching perfectly with a quadratic polynomial of some kind. And we can formulate this polynomial and then use the formula, Newton's forward difference formula, this formula, we can use it to find some in-between values. So what kind of values do we want? Let's suppose that we want, for example, the value of the function f when x is equal to 2. Okay, so what do we know about the point 2? Well, we know it's right in between 0 and 4. So if this is x0, then this is essentially the x0, and p in this case is equal to 1/2. Remember, we agreed that p is a measure of the distance between the points. So p equals to 1 is a whole distance, given that all our points are equally distant from one another. So p equals to 1/2 is exactly the point that we want, x equals to 2. So what we do is we take the value of p equal to 1/2 and we simply plug it into the above formula. And we've already got these terms. We've got the delta f0, we've got delta squared f of 0. So essentially all we have to do is we take the value of p, we plug it here, here, here. We don't need the third order terms because on the second order we already have everything kind of matching, and we basically plug that in and get our values. So we calculate the function at x0 plus ph, and so we take these values, and essentially at the moment it's these sets of values. So we take first of all the f of 0, which is also this value 3, so we say 3 plus, then it's p times delta f of 0, so it's 1/2 times 56, so that's 1/2 times 56. And then the slightly more complicated p times p minus 1, so that's 1/2 multiplied by half minus 1 is minus 1/2, divided by 2 factorial multiplied by delta squared of f of 0, which happens to be 160. Multiplied by 160, and the value that we get is 11. So that's the result for calculated at x equal 2. Okay, so let's try something else. Let's try a value which is further down the line. Let's suppose we want to calculate the function at x being equal to 11, for example. So 11 is somewhere down here. It's not exactly in the middle, but it's close. So what we're doing is, instead of taking these sets of values and setting p being equal to 1, 2, and 3/4, what we're doing is we're essentially just taking these values. We're taking the value starting at 8. So we're taking this set of values. Well, without the 8, obviously. We're taking this set of values and we're using that instead. So we're setting p equal to 3/4 because it's 3/4 distance from the 8 here. So we're essentially saying that in this case, the function at x equals 11 is equal to the following. So once again we take the 275. So we take this value 275 plus, and then it's p, which is 3/4 times 376 plus, and then it's 3/4 multiplied by -1/4 divided by 2 factorial and multiplied once again by 160, which gives us a value of 542. So this is how you apply Newton's forward difference formula.